Thank you everyone for coming in today. My talk is going to be about power management for VLSI systems and education perspective. And just a quick introduction, my name is Ayman Fayed and I'm an assistant professor at Iowa State University for the past 3.5 years or so. Before that I was at TI for about 9 years, and this summer I also have a TI badge, so it's cool to be back. So I'm actually here for TI, not part of the summit, believe it or not. So. Now the reason this presentation came about is because of the issues that I've seen after going to Iowa State doing a lot of senior design projects with TI that is related to power management, chargers, things like that. And that every year the same story repeats, that the students are unable to finish the project towards the end of the year because they spend a great deal of time learning what power even is. So I found that there is a serious issue related to power management education that I faced even when I was at TI, when we were trying to hire people who have the slightest idea about the topic. So what I will discuss today is a little bit of, what power really is, because, that's not something that is really known to many people. Why is it becoming a very important issue or a very important area these days? And also the problem of power management and formal education, which is a very interesting problem, and what I'm trying to do to address that issue because it's really frustrating. So power management, that word means a lot of different things to a lot of different people depending on who you talk to. When you say I do power management, people come up with all kinds of great ideas of what power management is. So this is just a quick summary of what it means. So if you talk to a system designer, for them it's a task-oriented issue, right? What's turned on, what's turned off in the system based on the functionality or whatever it is that you're doing. If you talk to a digital designer, it's all about dynamic voltage scaling. How do I change my power supply depending on the speed I want to run, and so forth. If you talk to a chip architect, it's all about power delivery. I have a limited number of pins where power is coming in, so how do I distribute that to everybody in the chip? But if you talk to people like myself, an analog guy or a power management guy, or most people at TI, when you tell them I do power management, what they think about is not the problem of managing how power is being used or conserved. It's really about how power is being converted. So if you do power management, that means you do linear regulators, switching regulators, that kind of stuff. That's what it really means for most people, the word power management. The basic task, just for the people who are not familiar with this, but basically in any power management unit, you have several energy sources coming into your device, USB, AC adapter, whatever it might be. So power source selection is a big thing that we have to do. Load sharing, if I have multiple sources coming in, how do I really share my load among these different sources for efficient use of power? And the biggest thing, of course, provide regulated power rails to everybody in your system. Supply level management, so the digital guy, when he wants to change his supply, he just wants to change it. He doesn't actually do it. He just sends you a couple of bits, and it's you who have to do it for him. Battery charging, engaging, leakage management. When I shut down the system, how do I really manage the leakage in my system? So these are all functions that the power management unit will have to deal with. The basic circuits that we use, and you don't have to worry too much about this, but we have what we call a switching regulator and a linear regulator. Those are the main circuit topologies that we use for providing power supplies to chips. So switching regulators can step up the voltage, step down the voltage, and they're quite efficient in terms of power, but they're very noisy and expensive. Linear regulators they're a darling, for circuit people because they're so cheap, you can integrate them easily and so on, but they're very inefficient in terms of power usage. So these are the two main circuits that we use all the time, and students have just no idea what these circuits, as simple as they are, they just have no clue what these things are. So, re-emergence of power management. Why is power management all of a sudden becoming such a big deal? Isn't it that, good old power electronics? In universities we just call it power electronics. You say I do power management, they think you are working in wind energy, that sort of thing. Right? But it's got nothing to do with that. So it is not the traditional good old power electronics, and there are several reasons why the area is becoming so important these days. And the first reason is what we call the battery life challenge. We have all these portable devices now that we use, and you're always trying to increase functionality and reduce power. That's what we try to do. And the focus has been in the past, 15, 20 years in trying to reduce the power consumption of your system itself. So let's go and design the lowest power ADC possible. Let's go and design the lowest power transceiver possible. The focus has been on that. And of course comes with that technology scaling. Let's reduce, the device size, reduce the power supply. This way we can reduce the power consumption of the system and increase battery life, because battery technology is just not going anywhere. But this is yielding diminishing returns now. People were able to design the lowest power ADC possible. Any improvement just incremental. There is just doesn't seem to be such a big hope in reducing the power consumption any further. So it's becoming now that the only way you can reduce the power consumption further is by looking or re-examining the way you deliver energy from the energy source, the battery in that case, to your system. And that power conversion process has to be as efficient as possible to be able to improve the battery life any further. So that's why this area is becoming now a popular thing that people look at. And of course, the cost and size challenge. Anybody who does power management knows that these circuits require large passive components. They're bulky, they're expensive. If you look at anything else in the system, analog, digital, even RF, they're all successfully integrated in the chip, minimal external components, minimal costs, but power management is an embarrassment. It's the only thing out there that requires that big bulky inductor and big capacitance. It just doesn't look very good. You are the cost bottleneck essentially. Power is the cost bottleneck and performance bottleneck in these systems now. So, what are in general, the challenges there? Well, the problem with power that you have to be able to adapt to different types of battery technologies, and so forth. But I guess the most important part is the ability to generate a very large number of independent, well-isolated power supplies within a chip without having to use 100 inductors and 100 power supplies. And generally speaking, although in industry they would love to see power becoming more like digital libraries. So if I want an LDO, I want to have this nice library where I can just grab an LDO and just put it there, and I don't have to redesign the thing every time I move to a new SoC. Been into many, many companies in the past 3 years consulting about that specific topic. It just doesn't work. You're not going to have a library of LDOs or switching regulators that you can just copy and paste from like what you do in digital. Every time you do it, you just have to redesign pretty much the whole thing. So too much custom design goes into these things, and all attempts to try to standardize this just has not become very successful unless you are okay with over-designing so much and so on. But for SoCs in particular, it just doesn't work very well. You have to redesign every time. So power management and formal education. Well, basically, you have massive shortage in formally trained engineers in this area. And I experienced that when I was at TI, as I said, when we were trying to hire people. And it's very difficult to find somebody, a fresh graduate, who has any idea about the area of power. And we ended up at one point in hiring somebody who was power electronics background. And the poor guy struggled a lot, because for him a 20 microhenry inductor is okay. For us, a 20 microhenry inductor, that's as big as the chip, right? I mean, so you can't, the background is just so different. And what we also observe that in power electronics curriculum these days, they can't care less about power converters. It's actually the part in the course that they just cover in a week or two, and nobody cares about it. They're all about wind energy and all that, green stuff because that's where the money is. But I think it's a big problem, because it's really compromising education, really. I mean, this whole thing of running after funding and doing the things that where the money is really killing our education system, because people, as you mentioned, they throw away basic stuff. I remember at one point, they wanted to remove physics out of the initial curriculum. How could you remove physics? It's not even, because it's no longer relevant. Well, it's relevant for shaping the student mind and how he thinks, right? I mean, we can't say don't teach Bernoulli, rules, because it's no longer relevant to electrical engineers. But unfortunately, that's what you see in formal education, that just money controls everything, and oftentimes it compromises the quality of education that we give. So now if you study power electronics curriculum, even if you accept to take somebody from power electronics, The problem is that they have absolutely nothing about VLSI. They know nothing about SoCs or technology, anything related to the stuff that we do in IC design. They just have no idea. You open in the power electronics book, it's always that big transformer, discrete devices here and there. So even if they study some converter work, they just have no idea what circuits are. And that's a very common, even if you look at people who design, if you open up a fridge or one of these, you will look at it and say, man, it looks like these people are like 100 years backward in the electronics that they do, because they know nothing about VLSI. So that's one problem that you see. VLSI curriculum is as miserable as power electronics curriculum. Power supply for them is VDD. It's a line that you draw, and whether it's in the book or in the class, it's called VDD. You know nothing about where that VDD is coming from or how to deal with it, and even its impact on your circuit's performance, nothing. It's just not there. So when you look at it, power electronics doesn't cover this, VLSI curriculum does not cover this, and even existing VLSI power designers, so the people who do power in companies like TI and NTC and ABI, all these places, the people who do power are mostly people who do catalog product kind of power. So, you're dealing with things from no load to full load, you over-design for everything, you have no idea how your chip will be used. But when you're talking about VLSI systems and SoCs and these types of things, power is really a custom thing there, right? I don't have to go and design a regulator that works from no load to full load if that condition will never happen in my chip. So the fact that I know exactly what my system will do and how it behaves, it enables you to do a lot of cooler things. But as I said, catalog products, they are familiar with analog-friendly technologies, high voltage technologies, so it's easier for them to do power there, but you move them to a 45 nanometer node or a 28 nanometer node, and the technology is not what they're used to. So there is a challenge there that even the existing people who know the area, they don't know the VLSI technology either. So what's the answer to that, to solve that problem? Well, is the answer just more research groups in the area? That actually happens automatically because there is money coming into the area. So, a lot of professors who never done power before now are becoming power experts. Let's do power management stuff. But that doesn't solve the problem in terms of education, because first of all, typically the topics that they work on are advanced topics. They're not basic education kind of thing that you need to hire someone. And also access to limited number of students. How many students would a research group graduate per year? 2, let's say, 3? How many groups you have in the whole country? I would say less than 10. So when you look at the number of people that are generated in the marketplace, it's very, very limited if you try to resolve that issue on the graduate level. Graduate level courses can be very helpful, but my experience has been that even if you try to do graduate level courses in the area, it's already too late for undergraduate students who are not interested in doing graduate level studies. So they already have a bachelor degree in electrical engineering and they don't know what a regulator really is. So that doesn't solve the problem really. It's helpful, but it's usually too late for most students. So my opinion is that this must be resolved on the undergraduate level, because you have an access to large number of students that you can embed these kind of power concepts in their mind before they graduate. So the question is, should we inject VLSI in power curriculum or power curriculum into VLSI? That's another interesting question. Where should I address this problem really? It's hopeless case to address this problem in power electronics. Hopeless case. They just have the background that is missing in power electronics curriculum, and the students who get into it is just humongous. There is no way you're going to be able to simply familiarize them with VLSI and analog and digital and RF and all these things while doing power electronics. Is just a bad idea to try to resolve it there. And you also don't have power electronics faculty who know power management IC design either. So who is going to actually do it is a big challenge. So what I found is that injecting power into VLSI curriculum is a much more effective way of trying to introduce people to this area. Why? Because power circuits are generally quite simple and easy to understand, at least the basic topologies and everything. And for somebody who already knows analog and the VLSI, it's actually not very difficult for them to, at least that has been my experience, it's not very difficult to them to grasp these ideas in the process. But the question is that the VLSI curriculum is already very crowded. So, we hardly have enough time to teach the stuff that we want to teach in VLSI. So how do you really inject? It doesn't cost you that much time and effort to try to introduce that. So for instance, we have EE 201 that we teach at Iowa State, which is the most basic circuit course. This is the RLC stuff, right? Let's go and teach students about resistors, inductors, capacitors, and all these types of things. And I found that introducing a little section about using LC tanks for energy storage and reuse through periodic switching, which is a basic concept of switching power regulators. Very simple. It's just one lecture deal, and they get it very quickly. And you introduce them to the idea of switching power, that I can actually store power during a period of time and deliver it to a load during a different period of time. And that can happen in a very efficient manner. So you can actually inject that little module into your existing 201 course, introduce them to that concept in a very effective manner. Then we move to EE 230, which is the next class up, and this class is about system level design of various electronic functions. So we have an ideal op-amp, which you draw as just an op-amp, and you try to build systems with that block. We teach them what the basic op-amp function is, but we know nothing about the circuit design or the transistor level design of the op-amp at that point, but that's okay. And within that course, you can also introduce a very small section that you use an op-amp as a buffer to serve as a power supply. I mean, if you think about it, it's a very simple thing. It's just really a buffer. And you show them that this can be used to serve as a power supply. Very easy concept, but you kind of grab their attention that implementing a power supply is not a given, right? You have to actually do something to implement a power supply. So that was very successful too. Then we go into EE 330, which is a transistor level design of various analog and digital cells. NAND gates, AND gates, flip-flops, common source amplifiers, common gate amplifiers, these kinds of basic circuits. Very difficult to inject something useful there about power during such a hefty course. But what I found to be very interesting is that when you're describing the operation of these amplifiers, which is part of your course anyway, you can talk a little bit about the impact of the power supply in performance. It's very easy to say, I have a digital inverter, here is VDD, here is the threshold voltage. Well, what happens to that threshold voltage if VDD goes up or down, or if I have some profile in time? And what jitter means. And believe it or not, I was able to teach the concept of jitter in these digital circuits for an introduction thing by just telling them that, by the way, when you change VDD, something happens to the performance of these amplifiers and so on. So you raise the awareness of the students that they should not take power supply for granted, and they should be aware of the impact of the power supply on the performance of these circuits. So that was quite successful too, to raise the awareness there. And then you go into EE 435, which is basically a linear amplifier design course. This is when we teach them op-amp design, Miller compensation, all that kind of level of detail. And what's so nice about this course is that most people will focus on designing the op-amp. Well, an LDO, or a linear regulator, is nothing but an op-amp for all practical purposes. And all that you really need to do is that you say, okay, here is the amplifier that I designed. If I want to use this as a power supply, the same compensation concepts and so on, except that the power for your power supply now has to be variable and unregulated. So you introduce that some elements of linear regulator design in the context of that course. They just grasp it very quickly because they have to do it for a regular amplifier anyway. So you can introduce linear regulator design this way. So I found that these are small changes but big impact really, because even undergraduates who choose not to pursue power as a career, but they have a bachelor's degree, they graduated and they have some conception of what power management is and what power supply design is all about and why it's important and so on. So at least that awareness is very helpful for that. And interestingly enough, I can tell you that this is the course that I introduced in 2009, and I actually taught it several times since then, and it's called Power Management for VLSI. We try to entice the students, by saying, have you ever wondered where your power supply comes from and all that. This is a graduate level course that I'm trying to extend into the undergraduate curriculum. But the course has been actually quite successful, and this is related to the question that someone asked about whether STEM is helping or not. I'll tell you what I found to be helping. What I found to be helping is jobs and money. These are what kids are looking for. If that doesn't happen, I had a student who was a very good engineering student, and his senior year, that was before the economic crash. I mean, MBAs can't find food anymore these days, but at that time, that kid finished his bachelor and went straight to an MBA program because he knows he can make $200,000 a year right after he graduates from that. But with engineering, 60, who cares, right? So a lot of students think that way. They have a lot of loans that they have to deal with and all that. So if you don't emphasize, if we don't have an emphasis that science is important and science can give you a good life financially, you can stimulate whatever you want. It's just not going to work. That's my opinion. It's a little bit political, but yeah. Anyway, so, but this course has been very successful in the sense that the market is in real need for people who have some background in this area. In fact, I had maybe in the first time I taught that course, I had maybe about 7 or 8 students who ended up getting jobs at LTC, ADI, Broadcom to do power converter design. And the only background that they had is this course about power. And that was just good enough to put them in the job market and find good jobs. Some of them, their PhDs had nothing to do with circuits. Most notably, a student that I had, his PhD was in worms. He goes to the lab and measure, how worms. I mean, it's Iowa State, so they care about worms a lot. And he would go and try to, what happens if you put a charge on a worm and all that stuff. And I always used to complain and say, oh, I don't know if I'm going to find a job. Well, if you're doing worms, then I can't help you. And sure enough, he took that course. He ended up at LTC designing switching regulators. A guy who does worms for PhD. So the market the market needs people, a lot of people who have some experience, some exposure in this area. And by just one course, that could be good enough. I'm trying to do better in terms of producing more students that you can hire a TI at least, and he has the basic concept that you can train them to do these types of things. So thank you, and I will be happy to answer any questions if you have.
We do have a hard stop at 2:15, and you'll all be moving over to the next room for the next workshop. So I would like for you to keep the questions short, please.
Yes.
How did you manage to influence so many courses?
I just do them.
So you teach all those courses?
I do them.
Okay.
I just go into class and I do them. I mean, if you try to go through the bureaucracy and forget it. No. University is a very different environment than industry. And if you just follow that bureaucracy, and a fellow professor who actually taught me this, he said, you just do it. Just go and do it. And if you're willing to do the work and do it, nobody will bother you. Of course, it's not like you're changing the curriculum from, instead of teaching RLC, you're teaching worms. You're just teaching something that is still relevant. So adding these little things. And that's another reason why I say it's much more effective to try to insert these little modules within the existing framework. If you try to do something like brand new, then you have to justify a lot of things. If you want to do an undergraduate course, for example, that only focuses on power, good luck trying to convince the dean or the department chair to do that.
I would actually say it's worse if you try to introduce the small changes like you did in... I would say it's worse to actually introduce small changes like you did into other people's courses than start a whole new course.
What does other people's courses mean?
I mean, if the courses were under the control of different professors, so to make small changes to 5 or 6 courses, I would say would be harder than inventing a whole new one all by yourself.
Oh man, who cares? But basically what happens, you have that fundamental course. Let's say you're teaching, first of all, I mean, many of these classes I'm teaching it most of the time, so that's not, but of course you have to get some buy-in from other fellow professors who teach that, which is not a very difficult thing to do. It's easier to get the buy-in from a fellow circuits professor than getting the buy-in from somebody who does non-destructive evaluation, right? So it's always easier to convince your fellow professors to do that. And you just go and do it. And, if the other professor chooses not to do it in 1 year, then, what are you going to do? You're going to do it yourself when you actually teach the course. So a lot of these things are individual contribution, but so far I haven't had a problem doing it. Yeah.
Any other questions?
When you get a corner on the market,
You-
Iowa, and your university has a corner on the market, and like you said, students follow the money.
Yes.
So, I mean, every university has their own expertise. Faculty drives the expertise. And,
That's right.
and Iowa State will get known as this is where you go if you're designing your SLC for power management.
Absolutely.
They'll come.
Exactly.
So,
and we're seeing that. We're actually experiencing graduate students who are interested in the area. They come to us because, we started to get known for this type of course and all that. In fact, this particular course, not even in universities, I teach this course in many companies too, that I go like as a 3-day short course kind of thing, and we do this. So it's becoming popular on an industry level and also on an academic level, but it's all about the jobs, as you said, right? If people know that companies are interested in this kind of expertise, they will just do it.
When they start seeing students see a listing for $80,000, $90,000, $100,000 for a power management engineer, believe me, they'll get interested. And that's your point.
Oh yeah, exactly. I mean, if the job is there, the money is there, they will do it. It's very simple economics.
That's like RIT, just a war story. RIT is very, very good at formula race cars. Toyota comes to RIT to hire students. But I mean, so you got your expertise. Every university, every person here has their expertise, and people come to everyone's university based on the expertise and reputation.
I agree. Yeah. I mean, that's definitely true.
I think it's fabulous that we figured out how to do it with one.
Yeah, well, if you look at, as I said, the basic concepts of power are not very difficult to understand. Very simple, actually. It's when you actually sit and do the design, you start figuring out, oh man, this is not as easy as I thought it would be. But you can learn that on the job. This is how I got in. I mean, do you think that I studied power management in my undergraduate? I had no clue. I learned all that stuff when I was on the job at TI, where I had to get into it because we couldn't find anybody else who wants to do it. So I got into it, and that's how it happened. So once you have the basic concepts, it's very easy after that to be trained and pursue it as a career. Okay?
Thank you.
Okay, thank you. Thank you very much.
So you will all be moving next door for a workshop, Eagle Board workshop.